Welcome back. Well, I hope your test went well. We're going to talk about the chain rule, and to talk about this chain rule, to be very honest, you have to have done your homework and gotten very familiar with those rules we have so far, because this rule is the rule to end all rules. If there's one that's going to kill you if you're not prepared, this is the one. So, with all that said, let's go ahead and let's talk about the chain rule. And this has nothing to do with chains exactly, the kind of chains you're familiar with. I'm from the north where we used to have to put chains on our tires when it got to be bad weather in the winter. This is a different kind of chain rule. And if you are up to speed on everything we've done so far in this chapter, you're going to enjoy this small challenge. So what about the chain rule? Well, we're going to find derivatives of functions using this chain rule. And we're going to use the general power rule, which is just an extension of the first rule we learned after using the definition, which of course you hated. And we're going to write derivatives in simplified form, answer real life questions, or at least as close to real life as we can get. And then some basic differentiation rule reviews, the ones that you should know backwards and forwards. So without all that said, let's get on with the chain rule. All right, here's the chain rule. Yes, it's the chain rule. Now, why do we call it the chain rule? If you look at this first definition down here, and this looks like it would be written by Jeffrey Leibniz. I'm not very good at some foreign names, but if you notice this is the familiar dy dx, okay? Simple. Now this one is dy du, and you're thinking, what? Well, if we use u instead of x, we'd have dy du. That's very simple. The second one is du dx. Well, if you had u expressed as a function of x, then you can get du dx. It all works together except different letters. Now, if you put these two together, notice that it's like du would be canceling out. And that's exactly what you want to think of. The chain rule goes from dy to du, and then chains over or is connected to du dx. And if you do put those together with multiplication, the du's cancel out and you end up with dy dx. That might seem a little bit strange. At some point, I'm going to show you a couple of different ways to use the chain rule. The second one, also using the same person's notation, it looks like this. Now, first of all, what you have to realize is that this is a composite function. It's one function inside the other. For example, if we go out here, here's example number one, not the one we're going to use, but if we had an f of x, for example, and that was, let's make it simple. Let's say it's 3x squared plus 7x minus 2, and that whole thing to the fourth power. Notice here that what we've got is, if you looked at this from a distance, you'd see, oh, we've got something to the fourth power. Well, I can differentiate that, no trouble. But when you walk up closer, you notice, oh no, that thing inside isn't just x, that's a function itself. That's the key to the chain rule. You got a big function, or the function that works overall, because if you were evaluating this, you'd have to find out what 3x squared plus 7x minus 2 was for a particular x. And then you would take the fourth power. Well, that fourth power is the outside function. If you think of the outside function, and inside the parentheses is the inside function. So down here, if we look at this composite function, we've got an inside function, g of x, and we've got an outside function, f of x. If we want to simplify this a little bit, we could write it like this, f of g. You would have to find out what g was before you could find out what f of g was. And if you're going to take the derivative of this with respect to x, suppose, what you would do is you would first take this g, and you're going to take the derivative of the outside function, leaving this alone. And then you're going to multiply it by what's inside. That's the basic chain rule right there. Notice you've got an outside function, you've got an inside function. Both of them you find derivatives of at the right time. With a few examples and some practice, because this is very, very important. So you have to first find out what the inside and outside functions are. Then you're going to take the derivative of the outside function, and where these x's are on, oops, I meant that to be out, sorry. Got carried away by what I saw below here. This outside function, we're going to take the derivative of that, but everywhere we end up with an x in f prime, we're going to put g, the original g, not the derivative of g, g itself. And then we'll put that inside the derivative of f, where you see the x's. And when you're finished with that, you'll take the derivative of the inside function and multiply it times what you've already got. A little bit of practice, you can go back here and say, oh yeah, I see it now. You take it one piece at a time, and then in due time, we can work them like this too. You'll have two different ways of commanding the chain rule for yourself. So here we go. One advantage of the chain rule is using this notation, because the chain rule works like this, where dy du is the outside function, or y is the outside function, u is the inside function. Y outside function, shorten that, and u is the inside function. And actually, once you get those, because that's the key to everything, knowing what the chain rule is, next, find the outside function. What's that outside function? The thing that will be done last. What's the inside function? Now what you can do is, this is going to be written as y equals and a bunch of things with x's in them. U is going to be written the same way, but first of all you find dy dx. And what you're going to do is, where you see the x's, you're going to put u in there. So what is u? U is the inside function. And what you're going to do is you're going to take that and find out what du dx is. Then you'll put these two together, because dy du, now the x's that you had became u's, and then take that times what you found with the other derivative, and that is going to give you the dy dx that you really want. A little bit of gibberish for the time being, but I'm trying to set you up for success on this. Inside and outside functions. So another example perhaps. Well, let's not go quite so simple. Let's suppose we've got a function f of x. Now I'm going to sneak into trigonometry, but that shouldn't be a big deal because most of you have heard of sine of x. That's a trigonometric function. There's also cosine of x, tangent of x, and the other ones too. But basically those three. We're going to actually use a couple of these in the future just as examples. Not that you're going to use those necessarily in business or any social related activities. So let's suppose capital F of x looks like this. And we'll make this, okay, let's say the sine of x squared plus 5. How about that? Now, the inside function is x squared plus 5. Because if you were evaluating this, you'd have to find x squared plus 5 and then take the sine of that. The outside function would be the sine of x. Now if you call this u, that might be handy because down here you would call it sine of u instead. Here's a nice short version. This is the way I remember it the most. This is the chain rule. Excuse me. Here's the outside function. And there's the inside function. You're going to take the derivative of f, but every x that f has will be the actual inside function itself. You'll substitute. And then once you've got that written out, then you're going to take the derivative of the inside function, multiply the two together, and you've got the chain rule established for that function. Okay, folks, let's look at a real example. As real as we're going to get anyway. The first thing we need to do here is I need to check, make sure that pen's still working. Find out what the inside and outside functions are. So in one of our definitions, our two functions could be represented by y and u. Y is the outside function, outside, and just put out there, and u is going to be the, goofed, the inside function. All right, so what is the outside function? Well, if you looked at this from a distance, you'd see the cubing function. So I'm going to represent the inside one by just a u. So this is a generic one, but the outside function is a cubing function. So there's the outside function. So what is that inside function? Well, the u is the inside part. It's x squared plus 1. Now, once you've done that, you'll be surprised at how easy this darn thing can be. So, I'm going to do basically this. dy du, and then I'll find du dx. I'll multiply them together, and I'll sort of cancel those two, and I'll get the dy dx that I really want. Oh, yeah, you think it's not that simple. Well, surprise, surprise, it is. So first of all, let's start with that outside function. I'm just going to copy it over here. There's my function. Now I want to find the derivative of y with respect to u. That's dy du. We're just using u's instead of x's. No big deal. What is it? Well, if you've been keeping up like I keep begging you to, bring the 3 out front. There's u, and it's u squared. Okay, let's move on. How about u? U is x squared plus 1. All right, we're going to take the derivative of that with respect to x because x is our variable inside here. What's du dx? Well, u is just like y is in any other one. And bring that 2 out front. Here, 2x, there's my derivative. So what do we have here? What we want from over here is we want to write down dy du times du dx, and that'll give us our dy dx. It sounds oversimplified, maybe a little bit, but not too much. So watch this. Dy du. We already took these two functions, the inside and the outside functions, and found the derivatives. All we have to do is copy. What's dy du? Well, it's right over here. 3u squared. And we're multiplying them together. And we need next du dx. We've got that right here waiting for us. And that's 2x. So what do we have here? Well, this is going to give us 3. Now, we don't need this u here anymore. So what we've got is u is x squared plus 1. So there's the x squared plus 1. And that u is squared. Remember, this is that expanded with the u replaced. And then we've got 2x. And we're almost done. We'll move some of these together. Slide the 2x out front with the 3. And our answer is 6x times x squared plus 1 squared. Done. How about that? That's not too hard. There is our dy dx. Remember, get the outside function, get the inside function, take their derivatives, and then put them together. Simplify. Done. Just like that. Now, what's the other way that I sometimes do? Now, if you understand this, you might ignore this next part. So I'm going to start again. Y equals x squared plus 1 cubed. How do I get y prime alias dy dx? Well, the way I do it is this. I look at the outside function first. I bring that 3 out front. And don't touch that x squared plus 1 yet. You hear that? Don't touch it. Just x squared plus 1. And it becomes a 2. Okay, that's the outside function taken care of. But we're not quite finished because this inside part is a function. So now we take the derivative of that part. And the derivative of the x squared plus 1 is 2x. Slide those things together, and we've got 6x, x squared plus 1 squared. Bingo. Two different ways that are equivalent, but they look different. Pick the one that you like best. All right, moving on. I'm going to first clear this of the ink. Okay, where's my, there we go. Clear that. Okay, so that we don't have it cluttered up for these next ones. So here's a reprise of what we just did. There's the inside function, x squared plus 1. Here's the outside function, the inside function, and there's our final answer. Now, the general power rule. What's that? Well, it's the power rule that you knew before, just expanded a little bit. Just a quick preview here. If we have y equals 6x to the 11th, for example, you should know by now that if you want the derivative of that, alias dy dx, and a couple of other ways we describe it, bring that 11 out front, you've got 66, and x to the 10 minus 1 or or 11 minus 1 is 10. There you go. That's the power rule, and we're going to have a general power rule. So here, instead of having just x here, we have a function inside. But it works almost exactly the same, except that what's inside is a function instead of just x. But remember, x is really a function, but the derivative of just x is 1. That's why it looks so simple. So let's take a look at it using the chain rule. So what does it look like? Well, if you start with this, if you find the derivative, you bring that n out front. You write your function the way it is ordinarily. You subtract 1 from this, and then you'll take the derivative of u of x, the inside function. And that's what this says. Bring the n out front, leave that inside function alone, change the exponent, subtracting it by 1, and then take the derivative of what's inside, right here, du dx. That's the derivative of the inside function. Here's a real shortened version. Bring that n out front, subtract 1 from the n. Remember, leave that u alone, that inside function alone. And then out here, that's where you put the derivative of the inside function. So once you've got the basic chain rule down that we just talked about, the rest is pretty easy. Just the power rule and the chain rule thrown together to be big buddies. So here's another question. Now we're back to finding the equation of a tangent line. And we've got a function here. And you might guess what we're going to do first. We're going to rewrite that thing because the way it stands, we're in big trouble. Next, rewriting it, there's our 2/3, 2 because of this exponent down here, and 3 because 3 is the root, and that gives you the 2/3. The bottom is the root, the top is the power. And the inside function stays the way it is. We're fine. What's next? Well, start with the outside function. Bring that 2/3 out front. There's the 2/3. Take that 2/3 and subtract 1 from it. There's our new exponent for the x squared plus 4. And then, because what's inside is not just x, but a function, we take the derivative of the inside function. So that gives us the derivative. Why do we care? Well, remember, dy dx is the slope of the line that we want at any particular point. So if we want a slope at x equals 1, we'll put 1's in for these x's, and we can get the slope. So there's our derivative. Simplified, put it back into the radical notation. Now, we want it at x equals 2, so we put 2 in our original formula. We find y equals 4 is the one that goes along with it. The point we're interested in is 2, 4. And we found the slope for 2, 4 by putting the 2 where those x's are and evaluating it. We get 4/3. That is the slope of our tangent line. What's next? Use the point slope form. We've got a point, we've got the slope, we're in business. All we have to do is put those things in, and you can find we've already got that part. All you have to do is evaluate that point slope form to find out what the y-intercept is. And of course, that's also function notation. So it could be written like this, and you would be perfectly okay. Either one is good with me. Here's what it looks like. And here's, to me, is one of the fun parts of calculus, or geometry, or pre-calculus, whatever you want to think of it. Here's our original function, there's our curve, and here's the tangent line. Graphing these two on your graphing calculator, your TI-84 perhaps, this is really neat because you get to see the function itself, you see the tangent, and you see how it's exactly tangent to it at 0.24. Everything comes together with a graphing calculator quickly too. So, some simplification techniques. It's always good to have it simple, right? So, we've been emphasizing that, and then two examples show some nice simplification techniques. So, let's take a look at finding the derivative of this one. First of all, take a look at that, and what should it suggest? Well, the first thing you should notice is it's a product. Second thing you should notice is you're going to rewrite the radical part. So there's our original function above. We'll rewrite it so that it's in the power look. And then we'll split it up. Here's the first function. Here's the derivative of the second. Then we swap them. This is the second one. And this will be the derivative of the first one. Sort of moved around a little bit, but whatever way, you know that multiplication is commutative anyway. And you can rearrange these things a little bit. Finding the derivatives, you get this, you get this. Simplify it a little bit, you've got this. Notice that you've got 1 minus x, two different places. Now here's a challenge for you. I'm not going to do this. Let's see if you can get from here to here. I'll give you a couple of tips. One, notice that, well, first of all, you've got two terms separated by that plus. Both of these have x's at the front. The least common denominator, or the lowest common divisor, is x. X is the common factor between x cubed and 2x. So there's your x. That's a common factor. You're going to take that out of the whole thing. Also, you've got 1 minus x squared. Now this is where it gets tricky. We're going to use this as the common factor. The key here is that you can write this one in terms of that one. Now, the x into the minus x cubed is that x squared. And over here, you got the 2x. And we've factored out the x, so you only have the 2 left. And over here, you factored out the 1 minus x squared to the minus 1/2. So one thing to keep in mind is to get from here to here, keep in mind that 1 minus x squared to the 1/2, if you square this, you get the 1 minus x squared to the first power. Now there's 2 of these to that 1/2 powers. So there's actually 2 of those. If you factor out a minus 1/2, you end up with this. Try multiplying this back and see if you don't get that all over again. It's a little bit tricky. If you can get it, fantastic. If you don't, I wouldn't worry too much about that. Once you get there, though, you should be able to get this. This is just a rewrite from here to here. And this from here to here. You're just simplifying to get the 2 minus 3x squared. I do expect you to be able to do that. And there's your final form. Now, if you have trouble doing this, don't worry too much about that. It's not extremely important. You might get some different version of this that's equivalent to what's up here. That's what's important. Whatever form, as long as you've done the legal things mathematically, you'll be fine. Here's another one. Find the derivative of, notice you've got an outside function up here, and you've got an inside function. Now this is going to get tricky. So if you want this, first of all, the outside function says, okay, bring that 2 out front. Leave this alone. Oops. I guess I should get the eraser going here. Clean this up. Okay. Put the pen back in. Okay. 2 times 3x minus 1. Leave this part alone. X squared plus 3. That's a 1, not a I. And 2 minus 1 is 1. We don't need that 1 there. In fact, it might be confusing, but whatever. It's a 1. And then, remember, we have to find the derivative of what's inside. What's inside is, it's a quotient. Oh no! Well, that's not that bad. Come on. Get over it. So, how do we do that? Well, x squared plus 3, the denominator first. The derivative of the top, which is 3. And remember, this is the quotient rule, so it's a minus here. Then we'll swap roles. We have the 3x minus 1. And the derivative of the bottom, which is 2x. And on the bottom, what do we have? X squared plus 3 squared. Remember I told you, it's very important that you know how to do the previous sections using the previous rules, or you're going to be really lost. Now, what you're going to do is you're going to simplify this numerator, as we'll see in a moment here, because I'm not going to take it any further. You can take it from this point and take care of the manipulations. So, what do we get? Okay, so I've set it up there. I brought the 2 out front. There's our exponent of 1. Leave this alone. Make sure that's intact. Then take the derivative of the inside function, which we use the quotient rule for. There's our quotient rule. Should look the same as what I had up above. Then do some multiplication, alias simplification, and we end up with something like that. And by the way, take a notice, we don't need to multiply that out. Usually if we're using this for something, we're going to have a particular x we have in mind, maybe a 7. And we'll just take this expression, put a 7 in for the x's, and see what we get for that derivative. And an application. We're starting to wrap things up here. So we're talking about the Apple Corporation. And the sales per share, in case you happen to be a shareholder, are modeled by this function. And this represents the year 2004 to 2013. We want to find out how the sales per share are going up or going down or staying flat. How do we do that? Well, if we want to see how it's changing, that immediately means calculus, folks. So, and this looks easy if you know the chain rule and all the rest. So, we're going to use that model. This is the model. We're going to use that to approximate the rates of change in 2006, 9, and 12. Remember, that means t equals 6, t equals 9, t equals 12 when we get to that point. And then finally, would the Apple stockholders like what's going on? Let's see. Here's our function. We're going to find ds dt because the sales per share is changing. So we take the derivative. Notice we brought that 2 out front and we left this inside function alone. Then we took the derivative of the inside function. That's the chain rule. Simplify a little bit. And that's ds dt. And this is for 2006. When you put those in your calculator, there's what you get. Your shares are increasing. Notice the plus. They're increasing at 95 cents per year. How about 2009? We just do the same thing. We put 9 in there instead. And we end up with 657 per year. Hey, that's getting even better. And there's a graph of what we've got. If you're a stockholder, you're glad that you bought the stock back in 2004. You're getting a lot more for your money every single year. And last but not least, even if you've been keeping up and done well so far, it always is a good thing to review your basic differentiation rules. So here they are. Now it says next slide. It's actually slides because I did some special work. There's one, the constant rule. Constant means it's not changing. So calculus says the derivative is 0. It's not changing. Next, the constant multiple rule. That's where you just bring that c out front and then take the derivative of the function itself inside. Next, sum and difference rules. Well, this is almost a no-brainer. When you have two functions and there's plus or minus between them, you just take the derivative of this, you keep that sign that's between them. The product rule. Aha, this is where it started getting interesting. There's the first function, derivative of the second. Second function, derivative of the first. And with the product rule, remember it's always plus between them, as opposed to the quotient rule, which is this one. Notice the two big differences. There is a similarity between the product and quotient rules, but the minus is one difference, and the b squared on the bottom is the other difference. There's the power rules. A real simple one. Regular power rule, general power rule. Basically the same, except instead of an x, you have a function of x. And last of all, our hero, the chain rule, allows us to take things to another galaxy. Well, while we're still in this galaxy, I'm going to say it's been nice to be with you today, and I hope you have a nice evening. Take care of yourself, and I'll see you in class.